All right. So now today I want to just kind of do a quick math lecture. It might not be quick, but because I've done a bunch of things in this class and maybe they're confusing, and if there are people that maybe can just go along with copy written and just maybe do that process, but maybe some people kind of want to see maybe a bit more of a defense behind this little tilde symbol or this asymptotic thing where I say this function looks like this. So that's what this lecture's for. Okay, so the problem with this is, right, we're going to talk about asymptotic methods. All right, and this is my struggle for this whole thing because this is really like an entire field of math. Right? Not ideal for me because I have to do that in one lecture. So I sort of thought for a while on what could I do for you in one lecture to give you a whole understanding of what this stuff is. What are asymptotic methods, right? And how could I use them? So I came to this conclusion. I changed it. I was going to do a bunch of examples, but here's right. So one way I could do this, one way I could teach you all of asymptotic methods is I could just do a bunch of examples, right? That'd be like my option one. Question mark, right? And that would be up here, and I would make a series, or I'd do sort of more problems, and then maybe you would get some false sense of maybe what's going on, and then I could give you a problem that is not exactly like that example, and then you'd struggle a lot, and then it would just be a nightmare, I think. Right? So the problem with this approach for me trying to lump all of asymptotic methods into one lecture is there's just too many examples, right? Like a bunch of examples. It's like, so, right, there is an infinite number of problems. Right, so that's a kind of a useless technique, I would think. So what I want to so I decided really to just sort of like summarize right, the purpose of asymptotic methods. Right, summarize the purpose, the how, sort of the maybe let's say the algorithm of asymptotic methods for you. So you can maybe understand when to use them, how to use them, and why they're working. So I'll also say you might be annoyed that I don't just do a bunch of calculation examples for you, but I'm just saying I'm only doing this because I'd rather you just get the general idea and feeling of why you would use an asymptotic method and how you would go about doing it, as opposed to me just doing 4 math problems on the board and then you doing a problem trying to completely copy my math problem and it doesn't really match, and then you throw pens and you decide to give up on asymptotic methods forever. The other reason is it's almost like useless now to do these examples because of 3. Sort of, I had realized this in my own development of this, right? So in today, right. So today, right, I mean, if you've done Mathematica has just asymptotic integrate, asymptotic solve, asymptotic desolve. You won't understand what those are, so I'm trying to get across what those functions really are. Right, so you could even open up Mathematica and maybe you could just read the documentation. You can plug any function you want in, and Mathematica would actually do all your asymptotics for you to some degree. There's one point I want to just make in here, and that's this sort of qualifier right here. Mathematica sort of does all of asymptotics for you. It just has a something we'll call a standardized gauge function. But it's certainly good enough. So that's sort of my warning, because I have to try to maybe tell you asymptotics. There's a whole class at PSU that Mark will teach sometimes. It's just called Scaling Asymptotics, where it's an entire class just on this. And that's where you would do a lot of examples and see the inner workings of how things fail when they go right. But I only have one lecture for this. And more so, this is for, like, in your homework, right? I have one problem for homework, and you're just going to sub in a series and solve for things. And you could even I think you even do your homework in Mathematica. You just go asymptotic desolve. But the purpose and reasons behind this, I think, are important. So here's another thing here's something else I kind of like about asymptotic math, and that is sort of like in the history of math. Right, so just bear with me, right? I think this is important to know or like reason, so you don't just give up on math entirely. What do I mean by that? So like when we started in let's say math with like algebra way back in the day. After that, right, let's just say we have, right, calculus was the next biggest tool we had in mathematics to calculate things. It told us about slopes and changes, and it was like really a big heavy lifter in doing math. So like algebra helped sell farmland and do sort of like plot land calculations to help people do things in industry. And then calculus came along, and we sent people to the moon on integrals and differential equations. And then certainly, right, and then there's sort of computation. Right, I mean computation in the sense that like you can just have your computer go back to this world. Right, so the theories of computation are saying, while Newton people developed these mathematical ideas of limits and derivatives and et cetera like that, I'm just going to take a calculus problem and turn it into an algebra problem, just several of them. So you use your computer to just turn every single problem into just billions of algebraic problems that it can solve very, very quickly. Okay? So that's good, right? But sort of a forgotten stepchild is with another path, right? And that's this asymptotics field of mathematics. All right, so we have algebra, went into calculus for like useful computation, and then sort of these conform to each other, but then we just invented computers, and then computers can really do algebra, right, billions of times a second. So give up on calculus, just formulate a calculus problem, and then make the computer turn it into an algebraic problem, and it can do all the additions and subtractions and divisions billions of times a second, all good. And then really what happens is your job then is to formulate physical problems in a calculus setting, and then throw it into a computer, and it goes back in time and just solves it algebraically. But you have one other path then, and that's what this asymptotic stuff is, how I want you to use it in the future, right? That's this idea that you formulate your physical problem in the terms of calculus, differential equations, or integrals, and then before you throw it into the computer, right, and have it just go back to algebra, there's another path you can take. And that path is this asymptotics, right? So I like to think of asymptotics really as what? It's sort of it's a calculus of approximation. Okay? Calculus of approximation. And really the computation side of this is a calculus of approximation as well. I think you all know from your first homework that your computational homework 1, you all had even said that's lower bound, etc. is like, it's really this number or something like that. That's just really you listening to your computer too much, right? Because it took this concept of infinity and turned it into discrete things, and then like you got numerical errors from that, right? So in the approximation of asymptotics, you get a sense also of what you're approximating and what you're approximating with. All right? This process of my calculus problem into a computation problem, turn into the algebra problem, you then look at the error based on your, right, how you numerically integrated your equation or something like that. So numerical calculus is a field of studying what error did what's the error from going backwards? Can I bound that error? And then for asymptotics, right, it's sort of the errors built into it is the beautiful part, I think, about it, right? So here, you would have calculus computation, go back in time, and then for every method you would have to go back and turn into an algebraic problem, you would then have to sort of analyze what could your numerical error be. Maybe you guys have ever done like a convergence study that they say, and when you're using ANSYS or something like that, where you just run a bunch of things on a grid, and you go like, is the error going down? You make a log plot, and you go like, woohoo, right? That's this idea that you turn your calculus problem, solved a billion additions and subtractions a second, right? And then you do some study, right, on what was that error going backwards in time to like ancient math. You just have to discover it. But with an asymptotics type analysis, what you do is you sort of like say, right, you already know what your error is, right? You're already sort of assigning, well, up until this level of error, I know this is true. So it's built into the theory. There's no backwards. Sort of to form asymptotics, you have to state, right, there are qualifiers in asymptotics always saying, right, as this approaches this. And that's something to hold into your head. It's really the power of it. What else could I say about this? Right, and really even these things can inform each other as well. So I think, right, even if you love your computer a lot and it's the almighty God of everything, right, even knowing this stuff can help you with your computer. Because, right, your computer could, let's say, spit out a sequence of numbers. So in asymptotics, right, you could have a computer. Let's go like a big 1980s computer. I love these keyboards too, right? So this one, and it could spit out a bunch of numbers, right? For some sequence of numbers, it could spit them out. And they could each cost a lot of money to do. Right? And it could even be infeasible, let's say, to get this 10 to the 10 number. Right? Even the magical silicone god can't do it for you. You don't have the time on the planet Earth. It would cost too much. That is out of reach. But this theory can get you there still. So halfway could be computation. You're just generating, let's say, like a sequence or a list of numbers. There are even methods in asymptotics that let you handle this number right, asymptotically. You could write down an expression that would tell you this number to some arbitrary order of accuracy, whereas before you would be really guesstimating. Maybe just, yeah, so another motivation. And what I'm saying is like if you were to just do this way, right? Say I did have 500 of these, I could make a plot, right? And let's say, right, this integer n, so my scale will be log n, right? And let's say if I have all these numbers, like they end up sort of looking like this. Maybe they bunch up around here, they bunch up around here, right? And then you could sort of make a line, right? So this is going to be like, let's say right here I get to my 100 and right my 1 over n relationship. So actually, yeah, plot 1 over n. So the scale is 1 over n. So this, the one closest to the origin point, which is really when n blows up to infinity, right? That number, right, I could make some sort of line, and then I could maybe, let's say, get at this like limit point. But you wouldn't be able to do it that well. You wouldn't have a good, accurate description of it. So I should say this. So, right, so I would sort of extrapolate this outward on a piece of paper even, or even you could try and do it with your computer, and then this number I'm going to claim right, you would just sort of say, it's probably around there. And you wouldn't have any, like, right, you could maybe say, like, I'll give you 1 point of, right, 1 digit of accuracy on that. So this method of just, like, plotting a sequence of numbers that the computer spit out, it would just give you, let's say, you could just know this. You could just, right, it would be like, let's say it's 5.1. But you, like, no accuracy here. No confidence, really, because you're just sort of eyeballing this line right here. So I don't want to get into it, but some people are interested in it. I love this concept of asymptotics as well, right? And just maybe for a motivation, I want to instill in you that, like, using the methods of asymptotics, right? So you partially use your computer to generate the list, but then using that list, you can write down I'm just sort of saying arbitrary numbers, but, like, it doesn't matter. You could actually just write down the list, however many, right, orders of accuracy that you would want. So it's sort of a very specific type of extrapolation. And it makes kind of sense because the problem with this method right here is, like, even if you did it in your computer, right, there's still too much uncertainty in the numeric way that you're interpolating these things. So if you do, right, you're really just doing this asymptotically with the methods of asymptotically. You're just having a better and better. You're just making an actual better and better precision of how to adjust this line to get the exact intersection for what this limit point is. Okay, so that's just another example of how the methods of this help you a lot, right? Even if the computer's the everything in your life. And then. Should I do that example too? There's one more. What I have. So calculus has asymptotics. They inform each other, right? And then also, right, sometimes this is just more effective asymptotic stuff. It's just more effective to think of things this way. Because computation, we can get analytical solutions, right, for, we can write down, non-trivial functions. We can write down, very mathematical statements. But then we still need the computer to calculate them because we will call them infinite series, and we'll calculate out every term of a series, let's say. And that would be rigorously like the exact, right? That would be rigorously like the exact answer. And there's a cost of having to compute that. That is, you don't know how many terms that you'll actually need to get, like, a correct answer. But with asymptotics, you can just calculate one term of the asymptotic sequence, and it will do just fine. You would know that as long as I'm only looking at this area of x, it would look. So okay, I'll just say what I'm thinking about in my head for this, right? So another thing about asymptotics. Right, so there's a differential equation. It's called Aries Function. It's a fantastic differential equation. I quite like it. It's a pretty simple one, and that's what it is. So, sort of, right, the way you solve this equation, right, is you postulate, right, you do a Frobenius method, as they call it. Is it Frobenius? Yeah, I think it's Frobenius, right? Or you do an inverse integral. The idea is you guess, again, you say, well, I'll say that y is equal to an infinite series, or something called a power series. Something like that, right? Where x is the naught. Right? If this domain, let's say, right, if this equation happens for x, right, is actually equal to, like, the semi-half plane, right? This would still hold. You would just say, OK, let me look at, OK, so now my power series will just look like this. Right, so I just took the x naught to be 0 here. Right? And then with Frobenius method, you put a little correcting factor right there. Either way, this is an equality that we put in there. The equality holds meaning, right? So when you solve differential equations like this, I'm not going to solve these, right? So that if I were to teach engineering analysis, I could actually do this and I'd have a blast. But I'm just saying the method is you make the assumption, or you make the assumption that I know what the solution of y is. I'm going to say this function is smooth enough that I can make a power series, and I just now need to figure out what the heck these coefficients are. And and it is valid to do this as long as you know for a fact that y, you're looking for a smooth function. Okay? So then you would do this, and then you would have some crazy, right? You would do this, and then you would solve for what every one of these a n's are, meaning that you could then write down a formula, right? Whatever it is. It's usually some nasty thing. I think for Aries, it's like there's a factorial, and there's a gamma in there, et cetera, as well. So the idea is you can at least write it down, so that for every n and for every x, I can assign a term in this summation. And you could do that, and then you just define that thing. You just define this beast over here, something called the Aries function. And there's two of them. There's two linearly independent Aries functions. I didn't think I'd write down. So then once you do that math and you do all of your figuring out the coefficients, et cetera, you could then say that, okay, well then y is equal to, this is just nothing but this, right? And now that's sort of the beauty of Aries functions. So there's work that goes into these definitions of the Aries functions. You did it because you know there's an identical equality that you put in there. You figured out what the ANs are. You looked up in a table. And then really, every time you see a differential equation that looks like this, you can just go right to the solution. This is exactly the same thing, right, as if this wasn't there. Okay, so if you're if you're unsure about this, right, if you look at this differential equation, all I've done is I've taken the x out. You can sometimes always write down that solution, right? And you just go, okay, so I know the form of this one will look like this. So you see there's there's not really a difference in these methods, because sine x and cosine x, they also have power series expansions. They have simple ones, but they're still, right? You can still express sine like this. So this notation, or me writing bi, the Aries function and the other Aries function like this, there's no difference from this. This goes back to this idea that definitions of functions can be differential equations. And then just the representation of that function is like its own struggle. Right, so these end up being quite nasty functions. Right? They have these large power series expansions. Okay, so this is sort of so then AI actually has this definition, where all of these coefficients are known. You give me an n, I can tell you exactly what the coefficient is, what this Aries coefficient is. And then same with this bi. These are infinite series. So then the thing is, okay, if I'm evaluating this function, how many terms do I need to be accurate? Right? I mean, how do I really need to get to infinity for this to be totally correct? I only get equality if I take an infinite number of these terms for each of these functions. So is that good, right? So that's fine, but the idea is this does go back now to this computation thing. So this is now I have a calculus problem, that differential equation. I figured out the solution, and I'm back to a computation issue. Because now I do need to know, right, sort of how big does n need to be? How many terms do I actually need for this like series to give me the correct answer? So then the beauty then of like you sidestep that and you go, well, what if I'm only looking at values around some sort of point? Right? So the thing about this representation is any x that you give me, it could be 0, it could be 5, it could be 10, it could be 100, right? This will always be true. The question is just then how many terms would I really need to be effective at that? But then you'll see in this method, right, in these asymptotics methods, we also can say, we write this little tilde, that this function, this Aries function, really just looks like, I say looks, right? That. And then you put this qualifier like this. So I like to motivate things, so maybe did I get this right? You notice I just read these all, right? But the purpose is, right, the idea is with the qualifier of this. Okay, so what are large values of x when I'm evaluating this Aries function and the independent Aries functions? Right? I mean, and you would solve the C1s and C2s with boundary conditions. And then again, right, so then there's even issues of like I have to evaluate these functions at specific identical points. So even to solve for these boundary conditions, it can be problematic, right? Because you need to know the function at an actual point. Like even right, getting these values at an actual point, you need like an infinite number of terms. And there are different expansions. So this is just the large one, but I like this example just for this. So I'm going to get rid of my logic loop. So then there's this neat thing, right? And this it's like so this is like what they actually look like. So I think this is the BI. And then actually just using this one term asymptotic expansion, right? It ends up that it's not the best approximation like around here. But here, this is what amazes me, and I wish I was told this more. So, right, like before the value 4, it's not the best approximation of what this function looks like. But like after 4, I think this one like goes like this. Boop. Now you see the green and the red. So even though that in my asymptotics like expansion where I said that I made this qualifier saying I'm looking for the asymptotic expansion, which we'll talk about, as x blows up to infinity, and I just look at the very first term of it. One term, right? The very first term of it. It matches up perfectly after the value 4. Now 4 certainly doesn't sound like infinity to me, but it ends up just because of this, that it's like that. And that's usually how it works too, actually. The first term of these asymptotic expansions for either is infinity, right? It doesn't actually have to be like that large of a number to be a good approximation. It's right. It's like, you know, right, and it ends right. So after value 4, right, error. It's like below 1%. No, wait, much less than 10%. Right? The error between these two functions of just taking as many terms as I want and just using this one for large infinity, it just perfectly matches up. What else is the benefit of this? The idea that this little asymptotic expansion thing tells me the form of these functions and what they look like. right? This is not informative at all. Aries is some power series expansion with a bunch of coefficients and x to the n. It certainly doesn't like let me, kind of get a feel for what these special functions look like. But this does. So in the asymptotic expansions, as x goes up to infinity, and that's the amazing thing about this, infinity really just means past 4 in the case of these expansions. Sometimes they're different. But now, with this expansion just in the 0th order term, you get an idea for the form. You can sort of, in your head, after you do one of these, say, function looks right? Function looks like this, right? And that's this concept right here where these look like these exponential functions. They're just normalized by this power, right? So then if you're just at your desk or something like that and you see like an Aries function pop up, you can just pop this into like you can just pop this into your calculator or something like that, or even just whip it, right? Just quickly on like a command line or right, some Python program, right? It's just sort of first order things for plotting are just much easier. But they come with this qualifier that you need this infinity to occur. So here, notice that, right, this equality, I don't have any qualifier for this equality here. This is true for any x. Not question mark, it is. It's true for all of them, which makes it difficult. The fact that I have no restrictions on this equality, right, means that this is true for all of the x that the differential equation held on. So that's where you get a lot of, you have to assign an infinite number of coefficients in this series. But with an asymptotic series, by qualifying by qualifying this idea of around x or as x goes somewhere, you get more information because of this qualification. So in asymptotic series come with a qualifier saying the function looks like this if I'm going to infinity or to 0 or to 1. It just has some qualifier. But that's okay. In my book, that's a lot better. Because whenever you're like really, whenever you're really, trying to evaluate some type of function, you always know where the function is going to look like. And this is letting you know it basically looks like this. The Aries functions are amazing examples because they have rough ones around 0, but when it comes to positive infinity or negative infinity, they do really well. I think I have one. Okay, I'll do the best. So then I have another one as well, too. So even there, even there, just in this lecture, just the idea that Aries functions look like an exponential divided by a power. So where's my Bessel one? Oh, I like this one. So a Bessel's function. So how about Bessel's? This is a J. I write my J's kind of weird, I think. Sorry. It's a J. So J0, really a J alpha. That's how you define them. So similar to the Aries function, Bessel's functions are the solutions, or a solution, of this differential equation. Alpha squared f. And then the condition that, what was the condition? Yes, you want a finite at the origin. Don't worry about this too much. This is just something that arises when you do the same power series insertion. Okay? So same thing with the Aries function, right? You say, I know what this looks like. I'm going to say it's smooth enough that this behaves like a power series. I set it equal to 0. I say it's finite at the origin. And I do the same, not z. I do my same thing just like that. Again, you're seeing the same thing. You have nasty differential equation in there, right? You go, I just know what the solution of this looks like. It looks like a power series like this. And then you plug it in there, and you do a bunch of math to figure out what these coefficients are. When you do that, right, you end up getting this. What do I have? Okay. So for alpha being equal to no, not equal to 0. Do the general alpha, actually. So I'll just even write out ones now. A gamma function. If you don't know what the gamma function is, don't worry. That's fine. I'm just trying to express to you the power of this. So just the idea. These are reals as well. Okay. So this is what you get if you do your whole substitution of this. Frobenius, etc. Blah blah blah. I don't know what those terms are. Sort of this. You could even pull this out. Sort of. So you got your A's sort of in there. Some powers happening. This is I think Frobenius is needed there because of this little perturbed power right there. This is just saying for all even powers. So there's another one associated with this that has the odd powers. This power being the even. So there's a J0, then there's a Y0. So remember, I have AI, BI. Same with the Bessels. It looks like this. But just let's say we have this one here. That's what it looks like. You do a bunch of it, and then you have the same issue, right? You're still got to go like, well, how many of these terms do I need to evaluate to get a good idea of it? So let's take, right, kind of simplifies it, right? Because, right, when alpha is equal to 0, the gamma plus 1 is equal to the factorial. Okay, I didn't even have that. So this is just the general one, right? You could always just evaluate this one. In one case, right, when alpha is equal to 0, you can have the asymptotic expansion, this. And this is still something I want you to see, right? 1/4 pi with the qualifier, that. Right? So this is the Bessel's function. It's always true. It's going to be that, right, forever. It's valid for any x you give me, right? Any x you give me, it solves this differential equation with a finite condition at the origin. That's the solution. There's another one there as well. But it's not the most helpful thing at all. So the same thing, I take an asymptotic expansion, right, or I look at the asymptotic expansion of this Bessel's function, and I get this expression right here. And this is with the qualifier that x is blowing up to infinity. And what did I have? You do some calculations. I did this in Mathematica. You can compare them. And this one amazed me, actually. So looking at this actual series expansion, right? This series expansion's right. I need okay. This is so when I say infinite series, I'm saying this. This is my infinite series solution. That's what this one is. So if I'm just trying to evaluate the function at 5, just the value 5, actually even values past 5, you need at least 10 terms. You need at least 10 terms. This is actually I just did this for 5. So I'm trying to evaluate. I think about this. I'm trying to evaluate this function at 5. I'm trying to evaluate the Bessel's function at 5. That means I could just use one of these. I could use one term, pretty bad one, right? I could use 10 terms. So this idea of using 10, right, is I have a value 10 up there. And the alpha's off there. So then x over 2, I have a 4 values. That becomes 2. So then I have 2 to the 2n. So this is just a number, and the thing is, like, when you have infinite sequences like this, right, the partial sums are converging to one value. That's sort of how you know that you're in 10% error, right, is each of these values, if I take this to the 1, this to the 2, this to the 3, this partial sum of this sequence is converging to one value. It's converging to the limit, right, of this expression. So the idea is if I take 10 terms, I'm close enough to what that limit is. I'm close enough to actually infinity by taking 10 terms of this sequence. And that's for this. But this is just one term, right? So the asymptotic is just one term. So think of it as it's a one-term asymptotic expansion of the function. Okay? This one, so then one I think it was like x greater than 5. Right. So again, you have this same issue where even if I even my expansion, I was saying x goes to infinity, right? And it's certainly, and this expansion is more true as x gets larger and larger because all the methods are saying I've let x actually get there. But by having an actual analytical function to compare to, you get this even stranger idea that just the 0th order with the qualifier that I'm looking at values going to infinity, right? For values that are greater than 5, the first term is good enough. It's whenever x is less than 5 is your error starts getting worse and worse and worse. These are still special cases of the thing. That's sort of the biggest issue with asymptotics is it's littered with special examples. So it's hard. It's seemingly hard. But it's certainly, I think, motivating. Maybe you're in engineering analysis right now and you're doing this infinite series things and it's disgusting you. That's fine. So the beauty of, I erased it, right? And again, right, that's more important, I think. The idea that if you hear about Bessel's functions now, right, this idea that even past 5, they look like sines and cosines normalized by 1 over square root of x. That's what they look like. Right? That is something you would never get from looking at this infinite series. But it's still kind of problematic, right? Because even sine has its infinite series, whatever, right? That is priceless. Is this idea of the 0th order? These expansions tell you the form of the function you're trying to get at. You won't get that any other way. So that is the key. And then again, the other benefit of this asymptotic methods is, if you go back for the Jeffrey Hamel flow, right? We did this thing where we said that I'll look for a solution that behaves like this for large Reynolds numbers or small Reynolds numbers, and then it makes solving the differential equations easier. And then from that, you get an idea of what the function looks like. So that's that's sort of the same thing we did here. That Bessel's functions and that Aries functions I do, it's the same process I'm going to show you. The only difference is you have an analytical solution to compare to when it comes to those cases. Not the case otherwise. What do I want to talk about then? Okay, so where does this all start off then? Where do we begin in this story, right? We begin with the idea of comparing functions. Okay, so this is compare two functions f and g. right? I'm going to call this domain. Call it D, right? So two functions defined on some domain D. So it could be 0 to infinity, doesn't really matter. You have to sort of ways to compare them. So we say same order, or big O. There's big O and there's little o that's going to happen. So one comparison you can make of these two functions is you somehow know this. And it's really just sort of saying exactly what we said before. Okay. Definition. So we say two functions are the same order if this holds. Or I say finite. So everyone will hate me. I guess this is not a math proof class. But. So I say that we say f is the same order as g, functions g, if this holds. What is this saying? This is saying, right, I say f is the same order as g, capital O, big O notation, if there exists, right, if there exists some finite number k, such that this function is always less than, right, the maximum of this function. And then this is the idea of x, right, close to some number x naught. And there's issues with here, right? So then you could have x naught, this, right, be 0, x naught equal x. Finite, and you can even have x naught go to infinity. And then you just change this definition here as well. But this is sort of it's just the definition that we run with. This is called big O. Same order. These two functions are the same order if there exists some k such that this is a hold. It's not the most informative way to compare two functions. Why is that, right? Because, well, this issue, right, you could have a situation, right, you could have something like k could be like 10 to the 10, and this would still be true. So it would, right, so sort of magnitude and order are not interchangeable ideas, right? Right? Even though it's 10 to the 10, it's certainly less than infinity, and this would still hold. So it's just the existence is sort of a lame thing about this definition, and why mathematics is troubled, I think, with definitions. It's just sort of, right, this claim isn't as powerful as it is. It doesn't help you that much, but it's a starting point. And then you have another way to compare, and that's little o. So this is big O. So the other one is a stronger condition, and that's the idea that I can, right, is comparing two functions where one of them, it doesn't matter what positive exponent you do have, right, but this would still be the case. So little o notation, this is hard to say. Right, we say that f is little o g. If it really holds the exact same expression, it just means that for any positive number, for arbitrarily small, this still holds. And again, with this qualifier here. So this is big O, it's little o. Big O is nice. It just tells you kind of the order. It's not intuitive how that means. This one's certainly stronger, because this one is saying for any epsilon greater than 0, this will be true. So this function, the largest it can be, will always be bounded by this function to this. Right, sort of, right, functionally, right, it doesn't, right, so any points around here, right, it doesn't matter how big this one is. This is always going to happen. And there's different conclusions you can draw from these two different things, right? One of them being, right, any function that is little o to order 1. It's also little o to order 100. It's also going to be that. Okay, so a function is little o to any constant, right? What it means is that. You can see that just by this definition. If this number is just some constant value, however big it is, but this definition still holds, that means I don't really care how large that number is. There's always just some number, however small, that this must be true. Well, that means that, right, that this value has to be going to 0. Right? Another thing about this is you could say arbitrarily having epsilon being greater than 0. You could just have a limit. You could limit this further and further down all the way to 0. And then since this is a positive number, this would also have to go to 0 at the same rate. So it's two sort of ways to compare functions right now. Big O and little o. But they both require qualifiers is the biggest one, right? Essentially, even in this case, the limit definitions are sometimes a little easier to work with, right? So this definition really is saying the limit is k. Right? That's all this is saying. It's for any arbitrary thing, right? It's sort of the definitions themselves, but they kind of have an easier way, at least that the ratio of these two functions, right, limits to some constant value. And then for little o notation, that's sort of the other way to think about it, and that's how you can quickly get that result here. This one means this. So again, you have this thing happening in these comparison of functions of two different situations, right? This ratio is either 0 or some finite value. Both. This is still useful. This is still useful though if k isn't that big. So if k is not that big, right? Remember before it's not the most helpful thing, but let's say somehow you knew, right? Or or you're just saying right ad hocly. We got time for this, right? So this is sort of a thing where if k, we say, right, if k is equal to 1, then you have this shorthand of this. So if k is equal to 1, we say that the function f is asymptotically equivalent to g. Right? So then this definition, that has this sort of special other meaning. Equal to 1. Okay, we don't really care about the case when k goes to infinity, though, because we're not right. We don't right. There's certainly no statement you can make if this goes to infinity. Maybe there's sort of the inverse is just going to be that. But these are the helpful ones to think about. Okay. So point of caution then in these order notations of functions is to worry about differentiation. You can't. It doesn't commute with the derivatives of functions. So what I mean by that is okay. So this function sine of epsilon e to the x looks like this. You can show you can show that by the you can show that just this is capital O as well, right? And this capital O important, right? Because you're saying it's equal to the function k, and you could just make k 2, right? It doesn't matter as x goes to infinity. This definition still holds anywhere around there. so it's still the order 1. So in like your problem with the capillary jet going there, you had the cosine of the internal thing, but you could just say that function looks like this. So the sine, even though x is going to infinity, it doesn't really settle down to any sort of limit. It doesn't ever settle down to a limit. There is just, well, it looks like a constant 1. So knowing the definitions, right, you have sine would be over here. The g is my actual, the g being the input of the O, which is 1. So that would be 1. And then you're just saying there exists some k that's finite. So, I don't know, pick 1.1, pick 2. Everything's satisfied, you can say something like this. But, right, importantly, not equal there. Does this make sense? So while I have this, what I can't do is I can't take the derivative on this side and the derivative on this side and push the derivative into the order operation, right? Because the derivative here right? The derivative of epsilon, if I push the derivative into here, right? What I'm saying, what these examples are showing, these essentially they're counter examples. Right? Right? So because this is now blowing up as x goes to infinity. So you have different now behaviors when it comes to differentiating things. And that's not just the case with a constant value either. So it's not the case that the issues only arise from there because you get this 0 behavior. It's also going to be that case, right? Let's say you have x sine 1 over x. Okay, so this function, as x goes to 0, right, it's going to look just like x. All right, because this one doesn't really matter as I get really closer and closer. This has awful properties for many, many reasons. But this function, right, it looks just like this onslaught of like, but this idea as you go. No, I think that's infinity. It's infinity. Okay. But then same situation. Right, so in this example right here, it's not the case that all order 1 functions you can't commute with differentiation. There are still counterexamples where even if one is ordered like a function of x, it still won't hold. Right, you're getting opposite things. You have divergence in this term as x goes to 0. So it's not a case. I can't push the derivative inside, right? Well, this was order x. I can't take a derivative and push it through the order to get 1 all the time. It's a conditional thing. It works sometimes, though. Right? The thing is, though, it usually works with polynomials. So it will work for polynomials, and you can show that just by the definitions. Extra credit. Go ahead and prove that to me, that using the definitions of capital O, that I can commute the differentiation if I have a polynomial. Expression. Same thing with integration too, right? So even so, if I have f of x is the same order as a function g of x, right? You can't conclude in general in general, you just have to be wary of that. So in general, it works for polynomials, and it works for other types of function behaviors. I think exponentials work too. It's just the idea that you need to have, there are smoothness conditions on the functions themselves such that you can push those differential operators inside. So there's some restrictions on order, notation of comparing of functions, and calculus. Everything requires a qualifier too. What else do I have to say? Okay, so then this idea, here's one concept. You can show these, that, right, for any positive p, so z, even z to the 1, the natural log is the order of that as z goes to infinity. And you can show that by space definition. This helps a lot too, actually. Right? Again, there's almost a look idea as well. So this means, right, this is saying that it's just this definition of how to compare these functions. This is a fun thing. Okay, so we're moving along. The other thing that we get is it is transitive though. The other thing is big O. The other thing is that that big O implies little o, but little o does not imply big O. And you can just see that by these definitions as well. But this idea that if you do all your definitions using the big O notation, then they'll automatically satisfy the little o notations as well. So transitivity. So it is transitive. Right, and that is just this idea that you can prove that so you get a transitivity property. If this function is the order of g and g is the order of h, then f is the order of a. Then f is the order of h. And that's also just by combining these existence of constants which bound the function. So these are simply just important things of O that had to be shown and proven for this idea. So now we can order some functions is what's important because of transitivity. Okay. Sequence of functions that we have now. And these are important. These are what we call gauge functions. We have some sequence of functions. Right? It could go to infinity. It could go to n. There's an ordering using this little o notation. It comes from a transitivity property. So this idea, this is just saying I have one function, another function, right, and then go all the way to some other function. So these are just some sequence of functions. This means I can just keep going on and on and on. I can rank these functions and rank them, and I can make an ordering of these using little o, right? So given this sequence, I'll call this gauge. This idea of asymptotic sequence. Right, an asymptotic sequence is a list of functions that obey a little o property. Okay, so that is an asymptotic sequence. We'll call them deltas. And then we'll use an epsilon is called an asymptotic sequence, or a list of gauge functions, which are they sometimes referred to if they have the property. Two ways to think of this. Right. The next one, right. The next one goes to 0 faster than this one. Or really just the other way, right? And and this can also be said in little o notation, that is this. Okay, the limit one's kind of easier to think about, but then sort of this is just the first important thing of this order notation for us in asymptotic series. And that's this, that if I have a list of functions and they obey the little o notation given the definitions, then I have some list of asymptotic functions. So they're called gauge functions. What this is saying is the next one in the series, or any function that's later down the line, goes to 0 faster than one earlier on. And that's what this means as well in little o notation. So if I have some list of functions that obey this property, it's called an asymptotic sequence. Or in our case, we call them gauge functions if you're doing some expansion. But importantly, using all those definitions, people came up and you then prove, right, this ends up being a nice property. If I have any list of functions that obey this, and there are several that do. So here are many lists of gauge functions. I'll just list them. So you could have, I'm going to do n. So how about, here's a list of gauge functions. I'll just list them down, right? You could have just epsilon to the n as epsilon goes to 0. What does that look like? I have 1 epsilon, epsilon squared, epsilon n. So that means that delta n, right, is just this. It's not the most interesting function, but it certainly works. You could also have delta n here to be equal to epsilon negative n for going to infinity. That's still an asymptotic sequence. Notice what's very important about asymptotic sequences is this limit that you're referencing to where you're going. That's where the power of these things are, because there are many lists of functions that obey this property of ordering them. And that's this. If I have it to the n, this is one. But if I just change this epsilon to the infinity, right, this is also now an asymptotic sequence. And there's other ones too. I could have see, I always have to put some qualifier for these asymptotic sequences. This is still true. The list is just going to go on and on and on, and this is really the power series. So asymptotic sequences really generalize power series. They generalize these series. They used to be called divergent series, actually. But then people found, well, this was another neat one that's forgotten. Also an asymptotic sequence. So this is just the natural log as I go up and up and up and up for a power. How about, and then there's another one too. What's this one? Oh. This one's a little strange, right? So I have epsilon to the negative n, so this is dying, but then I have this exponent going to n. This actually is still an asymptotic sequence. There's even a combination of powers happening there. Interesting, right? An e to the n. No, I wrote that wrong. Sorry, e to the n. No, it's e. Sorry. Okay, e to the epsilon. Okay, So e to the epsilon, then e to the negative n. Also an asymptotic sequence. And then there's another one, too, which is the strangest one. It's called asymptotic jumping. And that is this I'll just give some lists. So this one where it's 1 epsilon, epsilon squared natural log epsilon, epsilon squared. And then you have epsilon squared natural log, epsilon squared, epsilon cubed, natural log epsilon, epsilon, and then on and on and on. Right. So this one's strange. This one is this one doesn't have the neatest matching. It's hard, right? The formula has a strange one to it too. But this looks like this one of 1 and epsilon, then epsilon squared. But you fit this other term in there that still obeys this property that the next one went to 0 faster than the bottom one, right? That it goes to 0 slower. This is as 0 goes to, yeah, and this is as goes to 0, right? So this one's strange because you really are popping in these extra terms to this sequence of functions as well. So all that to just say there are many gauge functions. All this to just say that's it. Trying to just get that across, that develop this idea that if ordering, you have some idea that the next one goes to 0 slowly the other one. You can then generate some arbitrary sequence of functions that obey this. And that gets you to an asymptotic expansion, or an asymptotic sum. Right? So then you can then just have an asymptotic sum right, where I take that list of functions that obeyed that property, and I just multiply them by any arbitrary set of coefficients. Right? This is a strange, right? This is the radical idea, right? You can just pick any list of functions that satisfy the gauge property or that are asymptotic sequence, or is an asymptotic sequence. And you can scale them up any way you'd like, and you can form this sum. And then this will still have the qualifier, right, as epsilon goes to some epsilon value. I'm using epsilon here because, right, there's always an epsilon that pops up. So then this is right. So then a lot of properties come up from like these ANs or coefficients. They're just numbers. They could be really large, right? But in the sense that with this, you get these you get these expansions, right? Where the fundamental, I say the fundamental theorem of asymptotics is that any function has an asymptotic expansion, and any asymptotic sum corresponds to some function with an equivalence class. Doesn't matter what that means. That's a definition here. But the idea is like you can always pose what this is, and then what's important is you say a tilde, right? So then using everything, you have this, right? You then get this rigorous idea that I can write down any asymptotic sum and then little o notation of the next gauge, right, the next, the n. This is 2. N, this would then be little o, remember what that definition means. It means it was leading down. So then if this then holds, right, this allows me to say this about a function. And it's pretty powerful. So the idea of going from equality to, right, how you go from equality of a function down to the tilde is the idea that it has to satisfy this other end of it must drop down to 0. Right? And I call it the fundamental sort of a theorem of asymptotic expansions or asymptotics because that's really it. That's right. The idea is just this idea: if you develop these gauge functions and come up with there's an ordering of some list of functions that you can make. We usually say epsilon to a power series. It's called the naive expansion. And then you can even prove that I can always postulate this sum, and I know that it will correspond to some function. And then the other way around works as well. That all functions have some asymptotic expansion, and then there are then properties of this expansion. Okay? So it should be very clear, right? You could pick any asymptotic sequence you wanted. Right? All this had to satisfy was those. So maybe you should understand now that since I listed so many of these, you have this idea that the expansions are not unique, right? Because you could pick different asymptotic sequences to do your expansions with, right? So this is asymptotic to many different things because they can pick several different asymptotic sequences or gauge functions. What is true, though, based on this definition, right, is that the coefficients are unique. That's important, right? You set some gauge series, right, in this theory. You have to just select, right, your asymptotic sequence with respect to this gauge series, right, with respect to this asymptotic sequence. After you set that sequence, this expansion has unique coefficients. How do you get those unique coefficients? Well, it comes from it's just coming from this definition right there. There's just a limit definition for every single one of them. And this is for one function, right? I had x's in here. Let me just use, okay, so maybe this makes more sense. Okay. Yes. So they had x's. So given some asymptotic sequence, the coefficients are then set. And they're set by solving iteratively this expression right here in the limit sense, right? Because you have to know what the sequence is. So given that sequence, you can always just keep calculating every coefficient. It's a program. That's what's instilled even in these Mathematica programs that do it for you automatically. So this is single variable, though, right? Okay. Always from going from single to multivariable is you get issues. And the one issue for multi is this. So then similarly, you have the exact same thing, and let's say we have some parameter epsilon. I say parameter, so I put this semicolon, but really it's just, you could think of it really as just write some two variable expansion. This then looks like this. Now instead of coefficient, right, values or scalar values, now you get this situation where they themselves are functions. And big important thing is this. This is the important conclusion on this idea of going to multivariables, which is what you usually do. If it was just single variable, you get the O notation, right? So asymptotically, right, I just know this is always dying off further. When it comes to this multivariable one, little o then changes to big O. I never appreciated that much, but that's really that's the hidden meaning behind these things. And if I had to, right, and I don't have the time, but I'm just trying to say maybe you understand what these little o's and big o's means. So when you solve differential equations, you have this capital O over here, not little o. And what that means is, well, I know what the next gauge function is, and I know that it's really very small, right? The multiplication in front of it could blow up. And you see that a lot. So be wary then, really, of your asymptotic expansions when you use them to solve differential equations. This is just saying functional forms match and match and match. But it does not tell you about the scaling of this, or the thing in front of your gauge function. Because this thing right here blow up. And that ends up happening sometimes. It's not that, right, so when you do this multivariable or do some asymptotic sequence to solve differential equations, it's not always the, right, it's not always the case you just keep taking more and more and more terms in the sequence and you'll get a better approximation. That comes down to that this could blow up. But what is ensured is as epsilon goes down to whatever value it is, they will meet up. They're all subtle things, but I'm just trying to get across these ideas. So this is sort of the idea. The grand asymptotic expansion idea is you need an idea of what O is, capital O and big O. You need an idea of what an asymptotic sequence is. I call them gauge functions. Usually it's used in the term. And then it's an analysis then on really these coefficients or coefficient functions. And the sequences in the series themselves have different properties. Now, what is the difference then of convergent convergent series and asymptotic series? Well, like I said before, right, a convergent series, right, the partial sums are getting closer and closer and closer to a value. So that's one definition of them, right? So one way to think of this is sort of like every n, every term after n is smaller than the previous, right? Asymptotically, the sum might be divergent, right? So if you leave off this term right here and just think of it as this, right? An asymptotic series, right? You can say that really that this sum can be a divergent sum. It doesn't have to be the case that this is always getting smaller and smaller, limiting to some value. For convergent series, right, if I take n, m, if I take the 10th term, the 11th term, the 12th term, the 13th term, whatever value that's getting to, it's getting closer and closer to just one number. It is not the case with the asymptotic series. They could either oscillate forever or whatever. But what I like to more associate the idea is that this idea that the closeness the closeness of this sequence, of this series, is controlled by these deltas and the point you're getting closer to, right? The closeness in a convergent series, right? So this idea of I'm getting closer and closer to the true value. closeness for convergence series is controlled by the number of terms you need, right, to get all the way there. And that's at issue with the Aries functions that we had before. And you're right. And this is the idea that really the power of these series are coming from that you are just selecting some arbitrary gauge functions or asymptotic sequences, and you're saying, well, my function asymptotically will look like this. And that power is then saying, well, I know as long as I get closer and closer to here, it will work out. Right? So the convergence, right? So with the convergence or the closeness of your actual of your approximation is controlled by things you're setting. Right? The gauge functions control the closeness. The number of terms control closeness for convergence series. It's very powerful. So I guess that's all like the guts of the theory and the purpose I want to get across for asymptotics. Right? If you look at asymptotics, when people write little o, capital O, that's what they mean. They have these definitions of boundness. And then this other idea that the little tilde symbol, it's meaning that my function looks like this as this number gets closer to this number in this sense. So they're powerful. Asymptotic series used to just be called divergent series, and people like Euler and other mathematicians started assigning meaning to even a divergent series, and then it kind of gained its own popularity. They don't have to be divergent, though. It's also very important. Every convergence sequence is also every convergence sequence is an asymptotic sequence, but every asymptotic sequence is not necessarily a convergence series. Okay, so that's really it. The fundamental theorem of asymptotics is this: any function, I can write this down, and I can assign meaning to it then. Maybe I really should say this. I put a tilde there. I go there. Boom, boom, boom. And then you just say that. So any function can be asymptotically approximated like this, given some asymptotic sequence. This will be true. Now, the power of this comes in multiple ways. That's just that. The idea is I'm just allowed to make these series and then do things with them. So asymptotics allows you, it does the sequence things, but it has, you can, it has a lot of use in solve polynomials. It helps you solve this abstract problem of find the x such that this is equal to 0. Right? It can calculate integrals that you can't write down. So it could say, well, classic one. It helps solve this. If you have exponential integrals, right, you can write out what this is asymptotically. So it can calculate integrals. So this is the idea that this right, integrals like this can't be written down in elementary functions. So you can't evaluate this to some term on the boundary, right? And you just this is your transcendental integrals, right, the idea. But with asymptotics, right, you can substitute, right? You can say that this integral is equal to some asymptotic sequence as some value gets to here, and then it would get you some expression, as long as you tell me what that sequence is, and then also can. And this is the thing that we've been seeing. Okay, and abstractly, that's just this, right? So then, where this is some function, right? So some function that just algebraically mixes up the x's and sets it equal to 0. That's what a polynomial is. What I mean by differential equation abstractly is here's some operator that just like mixes up the, right, that takes derivatives and mixes up the function and sets it equal to 0. So all these things can be attacked with asymptotics just on the idea of saying this and then determining what these coefficients are. So in engineering analysis, maybe you've been doing this, maybe you've done this in that other class where you've made the equality and then you've substituted in like the power series versions of this stuff, and then you've tried to figure out what every an or what every coefficient ends up being by some recursion relation. And that's these Bessel's functions and Aries functions. It's a very restricted case, and why is it restrictive? It's restrictive because we're trying to put an equality here. When I put the tilde there, I have this meaning of, right, functions in order that like, well, I know that the next function as well, and then you have this concept here that you then set these gauge functions. They're arbitrary. Okay, so then what's my little, let's do the polynomial even. You can see how this stuff works. You can take the asymptotics class, which is nice, because then you can really see these things happen. I'd like to teach that class one day so I can really go through every example. That'd be nice. But I'm just trying to get across the purpose. So then, where's my stupid polynomial? Okay, root finding. What do I mean by root finding? Okay, let's do a dumb polynomial, right? So here's this is sort of like, let's say you have some equation, a polynomial that looks like this. All right? So the goal of this now, right, your goal is find x. Okay? It's a third order polynomial. It's not 3. I mean, really, let's do it this way. Let's go. Okay, so there's some term right here, right? It could be like, it could be like 2.5 or 2.7 like that. They'd be like you scale it down and you have some coefficient there. Okay, so then what do you do for this? Well, you just do the exact same thing. You then go, okay, so this polynomial x, right? So if you were to find the function, right? If you were to write down, right? If you are to write down what this equation is, you're really writing down some root as a function of the epsilon. Okay, so if I found all 3 roots of this, just like the quadratic equation, what you're doing is you're determining the roots as a function of the coefficients. Okay, but I focus my eye on this one epsilon term, which could be small or just less than 1. We're going to say less than 1 for a reason, right? I could then think of this as, okay, well, I now have some, I'm trying to write down some function, right, like this. Hopefully you understand. If you're not, okay, so like the idea, right? So so think of it this way: x squared plus. So take a break, right? The idea of like if you're this idea that quadratic equations, if this was one. Okay, what are the roots of this equation, right? Well, we can always write down the roots of the quadratic equation. You can do it for a cubic equation too, but it's like really long and nasty. Okay, so this one, we go b squared 1 minus 4ac negative b plus or minus b squared minus 4a1c negative all over 2a. Okay, so then see how this one, it's giving you 2 equations, but right, this is still an x, like let's say roots. So I have a 1 and a 2. Right, this is a function of an epsilon value. So the idea of writing down roots, you could think of it, right, as some figure out the function in terms of the parameter epsilon. So what does asymptotics say? Asymptotics says, well, asymptotically, if I pick the gauge functions, it's called naive expansion, like this. Okay, asymptotic says this. Any function will be asymptotic equivalent to anything with respect to some gauge function. Notice what I did here is I picked okay. What am I missing? If I had a quiz, I would always put this on my exams. What am I missing on this? You're missing, right? You're missing with this the qualifier. Okay, so you're missing the qualifier that epsilon is going to 0 in this case, right? If it goes to infinity, it would be called singular, and we could do another example like that. But that's, right, certainly a different issue. So this is what's going, right? So if epsilon's a very small term, you put this qualifier on there. And this qualifier is why I pick this epsilon to the n. Right? You have to have these qualifiers when you use this. Right? As epsilon is getting smaller, right? As epsilon gets smaller, I know that these terms die off asymptotically. I know they obey that gauge function behavior. Okay, so if it's really small, right, you can just do a one term, right? Okay. This is what that is, and I'm just saying all the next terms look like this. Right? So you could carry this through all of your algebra, but it doesn't help. It doesn't really help you. You can do the products. The idea is you put this and you plug it into all of these things, and then you collect terms, and the order term will behave in that way. Okay? So then what you have is an x and then here we will have a 3 this is all times an epsilon, and then I would have really 2. So really, this is then what you have to say is then, okay, well then, if this is little o and it's 0, so then this actually has the same relevance as it goes to 0, so that's gone. And then, right, this means that these have to be 0. You wrote down 2 more equations that have to then be 0. Okay? So then you can just sort of solve, right? Then you solve them. We're okay. So then solving this one, this is just, what do you get here? Well, that means maybe you want to see that, right? So this is sort of, this would be x1 squared plus 3. Okay? So I have 3 roots here. I have 0. That would satisfy this. I have negative I. Okay, these are 3 roots. Complex. Will always work out that way. Okay, so then notice how this one now has all of these x naughts in there as well. So then, moving on, we'll solve those. And you get 2 terms. Okay, so now I have 3. Okay. Okay, we know the x naught, though. Do I have that right? And we know x naught, because we already found it from this equation right here. Then you then just solve more stuff. Right here. Okay, so let's put for this root, this goes away, then I have one. Okay. So the real root, right? This real root possibility in this case looks like 1. And then what does this look like? So this would then be 3 negative I squared x1 plus 3. So then this becomes a negative 1. This becomes a negative 1. That's 1. So this becomes 3. So now I have 3 times 3. No, 3. Yeah, 3. Then I have 3 times 3. 9x1 plus 3x1. This is then I'm just really throwing these examples, right, just to show you this idea that everything really just came from what? I had a polynomial. I was trying to figure out this function, right, as asymptotically with epsilon. You pose this series, and then you plug it in. You can just continually chug along for more orders. Okay, but the other way to do this is just to write down any polynomial with this in mind, know what value you're going to put in there, and then Mathematica just say asymptotic solve. And this is just what it's doing, is it's generating these equations order by order, and then algebraically solving them symbolically if it can. And if it can't, well, we'll numerically solve that. Okay, so maybe sort of the culmination of this stupid polynomial example, right, is, I think examples are all, right, so then all of the roots, asymptotically, what did we have? Well, we have that it looks like we said up to this order, I can describe all the roots like this. So then, I mean, it's not that informative, right? So I have, it looks like 1, or it looks like so, right, if epsilon's really, really small, then it looks like this. You analytically now have like expressions to kind of tell you what these roots look like. That's the algebraic sort of example for this method of asymptotics. Well, what's the method? The method is you pose it as a series, you set some gauge functions. The naive expansion, right? No terminology, right? We say a naive expansion that's what it's saying. Because not always is this the case, right? It's called naive because sometimes this will fail because, right, similarly, right, the other valid gauge functions could be this. Right, so the idea is you could be missing like squares or expansions and half powers or third powers. And your naive expansion will show that. If you take the asymptotic class, you really just do a bunch of problems where like you really should have taken the expansions like that. But you can see that if you do more of the examples. Again, though, at this level, for what you people, for what y'all are doing, right, I'm okay with you just, right, when you're looking for asymptotics, you can just go asymptotic solve in Mathematica, right, or asymptotic def solve, and then you at least know what they're doing. You're not totally in the dark about how this number is being spit out at you. Is it a good number? Right? How do I believe it? And the important thing is you have an error bound because of the gauge function you chose. So that's also the thing. Right? Mathematica okay? So Mathematica automatically chooses the gauge functions for you, right? You're allowed to pick any epsilon naught or x naught, right? But it makes this gauge function that's the only thing about Mathematica with asymptotic solve, right? Is I've shown you that the idea that there's an arbitrariness on what you pick for your gauge functions or your asymptotic sequence. Mathematica gets around that by always using this gauge function. So as epsilon gets closer to 0, it's basically the same thing that we have right here. You're just allowed to put any sort of epsilon naught in there that you want. And it has a special case for going to infinity. So be wary that the idea is that there are other clever ways of doing asymptotics where you expand in some different set of gauge functions. There are many examples where the selection of your asymptotic sequence can make the problem simpler. I just don't have time. I don't want to go into that. I just don't want to go into that for this one lecture to somehow summarize all of asymptotic sequences. So there's root finding. I'm also not going to talk about the solving of integrals because I'd rather take more time on solving differential equations. So naive expansions. OK, so now we get to using it to solve differential equations. You've already seen me do this, though, right? OK, I think I'm missing a. No. OK, so this now idea that you always can assume somehow okay, you can always assume that some function has some asymptotic expansion like this, where this list of gauge functions is how I set. Again, remember that the naive expansion just is saying that this is just, right, this blah, 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 blah. And again, what am I missing? I'm missing this. Right? I say epsilon, it could be x, but epsilon's more important for differential equations with parameters that pop up in them. Okay, differential equations with parameters, very important subject, right? And then when you use it to solve, when you're using this method to solve a differential equation, there are two cases that pop up, really also in polynomials as well. So let's say you had this differential equation. Okay? And you know, you sort of know that. I mean, really this works out as maybe you've done this before in your homework. Really, you go through a bunch of setting up differential equations. You non-dimensionalize it to make them pure math problems. You get a parameter in your non-dimensional fluid flow problem. And this could be like a 1 over Reynolds. It could be a tabular number. It doesn't matter. The idea is it's just some number. You plug some numbers in for your fluids, and you go, I know it's a really tiny number. So then that would then go, it's a really tiny number. Let me get the asymptotic. Let me do the asymptotics on this, and let me see what the form of the solution looks like. Very good stuff. Right? And there's tons of these, right? You could have something like this. Okay? Similarly, let's say you did a bunch of non-dimensionalization, you got something that looked like this. Okay, where f's non-dimensional and all the derivatives are non-dimensional, but you have some parameter epsilon that pops up, plug some numbers in there, it's a really big number. So then you go, oh, OK, I want to do some asymptotics where I say this number gets very, very large. I'm just going to keep putting these things up there. You could even do this one. I mean, you really could even like sort of do this. This is sort of a troublesome one. Right? You could have that epsilon like is going to 1 or close to 1. It could go to some constant value as well. And this is where asymptotics does a really poor job, because you have to pick. You're really constrained then to pick that special gauge function of the power series. So it might not end up helping you. But I mean, like, great. So sort of like this way, you could think of like. For these ones, you could then have, okay, well, I'll just make my gauge function that I asymptotically expand about be this bad boy, right? And then maybe just make sure that epsilon is, maybe you know that epsilon's a positive number always less than 1, but you just know it kind of approaches it. So you have a flow problem where you do everything, you non-dimensionalize as third order, and then this number and this number is just always, you just know it's always going to be less than 1 because of some thermodynamic term, but you just at least know that. So then you can maybe do some asymptotics to do this. Okay, all of these have a property that they're called regular. Okay, and they're a regular problem because as epsilon gets down to 0, right, well, if this term is gone, if I consider the 0th order problem, as they say, right, if I think about the actual limit as epsilon goes to 0, right, this term is gone, I have this second order ODE. So the second order sticks around, and that makes it regular. So then you have other situations like this. All of these things I've put on the board. You actually could just go onto Mathematica and go asymptotic desolve, and it would spit out some answer for you for what f looks like, dependent on epsilon. It might tell you issues, right? So then you could have ones like this. You could even have more. I mean, same thing, right? These right? These are totally nonlinear ODEs. But as you can see, let me put one more in there, right? So let's even have like a 5th derivative. No, f to the 5. Okay. All of these have the property that they are singular. Now, this definition of singular and regular is sort of a, right, it's sort of, I've never found one that's like fantastically like satisfying definition. But singular essentially just means this, right? You're going to have singular problems if your small term in the limit is getting rid of your highest order derivative term. Go by that. And it really behaves, right? And there are ways to think about this as well in the polynomial senses, right? In the polynomial sense, okay? Right? Let's look at this one, right? This ODE would come with boundary conditions or initial conditions. It certainly would come. Let's say it comes with boundary conditions, right? So even if this is gone, I still have 2 equations to solve, and I can solve for my integration constants that way. That could be gone, but then, like, right, abstractly, you're always going to integrate twice. You then have 2 integration constants to solve for. Boundary conditions or initial conditions would get you there. Okay, so you can figure out what those constants are, given your other equations. Makes it regular, right? As this blows up to infinity, right? As this blows up to infinity, this becomes the most important term, right? So it still hangs around and still the most important thing in there, right? Notice how in this expansion, epsilon's going to infinity, so the highest order derivative term still matters in the limit, right? This becomes abstract. This becomes infinitely small compared to this term. You can see that by dividing out by it and get it that way. So it's still the same thing. You would have two boundary conditions, and you'd still be able to solve for your coefficients. In all of these examples, though, in the limit as this goes to 0, now I don't have my second order. Right now I don't have my second order. Okay? I just have a first order. So that means that I've thrown away an entire integration constant. So singular meaning the form of the solution as this goes to 0 fundamentally is different. In a differential equation, you need more experience in solving them, in a math setting to really get that the form is different. But you can always think of it like the polynomial in a polynomial case. Okay, for a singular setting in solving polynomials, you can have the same situation, right? What if I had, right? What if I'm trying to solve this? So, right, let's just imagine we just said, right, imagine we just did this, and this is this naive assumption. Okay, same setup, and then imagine we put in our first order. Okay, we just plug that in as first order, and then plug it into here. Notice what's going to happen, though, now for this situation, right? I'm going to lose, right? I'm going to now lose a root. Okay, so the always way to think, you can always solve the 0th order term, right, is always easy to find because it's just when this is actually 0. So x0 then right? So the 0th order equations gave me a starting point that was just 1 and -1. Bad news, right? Because I know that I need 3 roots. I'm trying to describe 3 algebraic roots to this thing. Fundamental theorem of algebra is that any polynomial you write down, right? If you write down nth order polynomial, there are n complex valued roots to that polynomial. So singular in the sense that the 0th order expansion, I have no starting point for the 3rd root. I only get 2 of these. I can't, right? Because all of my other ones are going to build off of these other roots. So that's the singular nature. And really the same thing's happening here. Same thing happening here being where at 0 you've thrown away the initial solution, so you can't recover that behavior. The solutions are fundamentally different in the limit as one you see all the time, but it doesn't really, it's sort of like we're going to go with that? I guess then how do you fix this? What did I have? I had this. Negative. So then the way we need to fix this is you need to rescale the problem. And I mean rescale, I mean seriously doing this idea of it's really a change of variables. So to fix this, we must do a change of variables. I'm just always going over time now. I'm sorry. Okay, so we need to rescale this. And what rescaling means is I need to find some y. Right, a scale variable. So I call it a magnification term. All right. So then, right, it's really, I mean sort of just, so I have y. Okay. So if this is getting very, very small, right? If this is getting very, very small, I need to zoom into x. So that's why I say this magnification term in there. So then, right? So I say I need to scale up x by some magnification amount. I plug this in there. Now I get this epsilon. can I have a and the y variable and then at this point in order to determine what this m should be, there's this idea of balance. Okay, and the balances are this idea of, well, in this magnification, which other term should stick around, right? So this other term sticking around is just the scaling thing that we've done. We've picked two terms and compared them. And then even in a polynomial case, it's exactly what you're doing right here. You're saying, well, as epsilon gets very, very small, right, I want to blow this up and maybe retain one of these other ones. So should I pick this one or should I pick this one? All right, so if we pick, there's really two options, right? So let's do this one, right? So if I say that this, right, if I say that this term and this term balance, right, this would just be saying that okay? And then if we plug this back in there, right, so that's this term and this term balancing. That then would mean that the rebalanced equation would be okay. So now there's certainly an issue with this balance because, well, if I have this balance occurring, as epsilon goes to 0, this term blows up to infinity, and again, I've lost the root. So that one didn't work. What else can we do? So we can balance these two then. So in this balance now, what do you get? You just have this relationship. For this and this balance, that means that, well, that just means epsilon is equal. Well, you put an equality here. Okay, so that means that the scale, I should magnify up by an epsilon. So then what do you have? Now you have epsilon all right, and then after you have this, there's issues here, right, of the balance, but then you just multiply through, right, multiply through the whole thing by an epsilon squared, 0 times this number, so that's fine to do, and then you just rescale the equation to then look like this. Notice in this polynomial case, I now have retained the third order root in the limit of 0. So there's no problem with epsilon going to 0 in this polynomial, right? I don't get an infinity in this polynomial as epsilon goes to 0. Right? That's important, that I don't have some infinity. So the same things are going to happen, same things will happen, just the same things happen for differential equations. So that's the singular rescaling. So then, to end, let's do an example of this singular asymptotic expansion series. But I hope, right, the idea you get, I hope I get across, maybe I hope I get across a lot of things. This idea that the asymptotic expansion world is just that. It's just you have the power to say that f looks like this asymptotic series, and then do a bunch of algebra to figure out the terms. That is it. So how about let's do a singular example then. I'll let you go. Here's some problem. ODE. Okay, here's a linear ODE, actually. I don't know why I picked this one. So this is a ODE, and it has some small parameter in there as well. And you want to write down the solution for all the epsilons you could think about. So same thing, right? Same idea. We go, OK, well, this function will have some series that looks like this, and I'll do the naive series. OK, this is some naive series. Instead of f, I have to do 0. So then what's your zero? So then you have your 0th order, right? So if we're just looking now for the 0th order equation, we will have this issue happen to us. Okay, so then the 0th order equation is right? Again, 0th order equations are always easy to find because you just actually make epsilon equal the limit you're considering. So this is okay, as epsilon small. So this is a small number. Okay, if it's a small number, you go, OK, well, let's look asymptotically what it looks like in this sense. Then I can at least get the small number correction term on it. You're allowed to do that. Okay, so then the 0th order is easy to find. You get here, and then this solution is this. You just plug it into Mathematica. I don't, or do it by hand. Rather, just plug it in. I mean, you can plug all this stuff in Mathematica. You just say this desolve epsilon to 0, get the first term, and you'd get this. Okay, so then this is the issue. The problem with this one is you've seen this one many times, and this is the singularity blowing up in your face, is that at 0, this is equal to 1, which is not 0. So this is a singularity issue that you're seeing. It's the idea that the solution is not recovering these. The solution doesn't even have the same form in that issue. And the only way around that is rescaling. We just need to know that is right. You just always, if you have a small term or some difference of terms in your differential equations where the leading order term has a vanishing term in it, then you have to do a rescaling of the problem. But this is what you end up doing. Essentially, what happens is okay, we'll just get to it. Okay, so now we need to rescale the problem because we have one part of it in the 0th part, and that's this part hanging around here. It's the part when this solution is actually 0. The solution looks like this. But for any for any non-zero epsilon, I have a totally different rate. For any non-zero epsilon, this function won't even satisfy the boundary conditions. So we need to rescale this. So then we'll go, OK, well, this is this. So sort of the fundamental idea is that for singular asymptotics, when you have this issue of vanishing high derivative and they're singular, you go, okay, I'll solve the outer problem, the inner problem with a rescaled variable, and subtract off the common part. I showed you this in the radial flow. Really, these come about from a condition that you want these limits to be equal, so you don't want to double account, so you minus off a common term of those. All right? So then you just go through and try to figure out what the rescaling should be. Okay, so then I want to say eta will be some y divided by magnification term, function. Boom. I don't know why I'm doing. I mean, this example is even linear, so I think it's a bit overkill to do it. But yeah. Oh yeah. Remember, this is capital O. I'll test you on that. Because you know that the next function looks like the epsilon. You don't know actually the growth, you don't know the actual growth of the next solution, though. It could blow up, and this is the idea of asymptotics sometimes being not the best the more you take. Big concept. Okay, anyway, so looking for a rescaling. All right, what can we do for this rescaling? I'm doing for rescaling. Scale these two terms. Okay. What did I do? I multiply through by an m. So I multiply through by an m. M. So I just multiply through by an m, and then next I scale this. So I want this to be order 1. That's what I multiply through it. Sometimes you do these things differently, right? You could have just said, I want to balance between these two things. I guess I did what I did when I was like, oh, multiply through. And then the only way that this could be order 1 is if m. So then with here, right? Sort of I did the step prior. Okay, so then here you go. You got a new epsilon, and it's equal to that. And then, if that is the case, that would mean my new inner equation to solve is going to be, it's going to be ui prime prime, okay, where a prime is equal to a d by a d eta. So it's that change of variables you have, or rescaling of problems. Prime, what do I have? And then all these epsilon. So then all the small stuff is on the left-hand side now. All right, so then I just have a differential equation for ui. Ends up being that. You get rid of another constant. You get rid of a constant by solving one of them, and you're left with this other one. And now this last constant comes from the matching condition. It's really the same boundary condition, it's just in the inner variable. So then this equation, right, you have one last constant to pick. This is coming from matching. Matching is nothing more than just saying these two limits as they go to the same thing should be equal. Okay, so a matching principle and what is it equal to? It must be equal to the common part. Sometimes it's called this. All right, so by then applying this and taking these limits, we have. Okay, so then this is this expression right here. So then, just take the limits, right? As 0 goes to 0, right? I get 1 plus a half, I get 3 halves. And then here, right, what's going to go down here, right? Here I have this going, okay, so right, this is equals to a. So then this constant a must be 3 halves. And then you fix that condition. And then everything's set from there. Everything's set. And then you have the full solution on 0th order. And really, I want you to think of it this way. Eta I write everything out. Just looks like this. So this is the solution to this differential equation asymptotically as this becomes a very small number. And you could keep going with this too. So you could, right, we only did one of these, right? We only did one of these and solved one composite problem of one matching condition. But you can keep going. And you can keep creating more and more expressions. And really what you end up generating, right, is for singular problems, for a singular problem where something vanishes, you get an outer expansion, or you get an outer problem and an inner problem, and you subtract off a common part. So the naive expansion is still, I think, conjectured to always be right? Because for a singular problem, you end up just you end up just generating this series. The outer, the inner, minus the common. Okay, and this, I should put this in there. Right, so that's really all I have there, right? Because eta is actually, right? Eta is a function of the expansion parameter. It's really a function of x, right? It's a function of x and epsilon. And that's your singular expansions. I don't have a singular for homework. If you take the asymptotics course, we will do examples of that. But that's it for asymptotics, right? Not really that's it, right? It's a very large subject. But the power mostly coming from those beginning problems where I showed that you could get the form of what the solution looks like. I mean, even this term right here, what this solution looks like as epsilon gets really, really small, even you numerically solve them, it's just right on the nose. Especially for like epsilon equal to like 0.1 or something like that. And if epsilon is equal to 0.3, you might need to find that second, right? You might need to get the second expansion. But it's just this process of continually chugging in algebra expressions and solving simpler problems. It's not just, but that's where it's coming from. So that's my one lecture where I get across maybe the power of asymptotics, to just simply, whatever your problem is, whether it's a polynomial or a differential equation, substitute in this form of the function that we know to be true given some gauge functions, and you'll get a solution. And that solution will tell you the right form. Okay. Take the asymptotics and scaling course, I think, because it's way better at describing this stuff. But really, the takeaway besides all soapboxes is I think I have some algorithm in there. Takeaway is just plug in, right? Just start there if you want to do it by hand. Or write down any differential equation and then go into Mathematica and say asymptotic desolve and figure out the problems from there. But it's very powerful just in the sense that you can understand the functional form of solutions for differential equations far better than a series. If you're doing that Frobenius stuff in the 551, I apologize, but this stuff's cooler. Just try it on your actual homework already. You actually know what the functions look like. It's cool. All right, I'll do a boundary layer next.